So we've seen that the value of a function f of x, y, constrained on a curve, level curve g of x, y equals 0, the level curve of g, we get a maximum of f or a minimum of f only when your value of f isn't changing in the direction of motion on g. And that occurs only when the gradient of f is perpendicular to the tangent vector, a vector tangent to t, at a given point. Also, the tangent vector, the vector tangent to the curve g of x equals 0 at a given point, is and has to be perpendicular to the gradient of g at that point, because the direction of zero increase has to be equal to the direction of maximum increase. So that t is perpendicular to del g, t is also perpendicular to del f, in order to have a maximum of f on the g equals 0 curve. And I should have said at a point of the g equals 0 curve, because we're talking about individual points along the curve. And we'll correct that with the full statement of the Lagrange multiplier theorem. So we conclude that since t is perpendicular to del g and also to del f, that del g has to be perpendicular to del f, so that, okay, one additional thing that wasn't written last time, because we want to make a transition to the next set of statements. Two vectors are parallel if one vector is a multiple of the other. So we're going to say, well, del f is a multiple of del g, and the multiplier is going to be lambda. So del f is equal to some multiple lambda of del g. If that's true at a point, then it's possible that you have a maximum or minimum on the curve. Now, we'll get the logic of this straight. It doesn't mean that there is a maximum or minimum, no more than a critical point of a function of one variable has a maximum or a minimum at every point where the derivative is 0. You can have inflection points where the derivative takes a value 0, but where the second derivative is negative on one side, the first derivative, and positive on the other. Okay, well, let's make a little more specific statement. We're going to say that f of x, y takes a maximum or a minimum, and it's takes, not take, takes a maximum or a minimum on a curve g of x, y equals 0 at a point x naught, y naught, and this point, since we're already saying we're on the curve, implicitly x naught, y naught is on the curve g of x naught equals 0, only if there exists constant number lambda such that del f at that point x naught, y naught equals lambda del g at that point x naught, y naught. So if you want to find maximum or minimum on a curve, and I probably should be careful about this because you could have absolute maximum or minimum, say relative maximum or minimum. Now I think we've got a statement that can more or less stand up. Of course, look at your book, look at literature, and so forth to really see all the details of how this is stated and the conditions. You know, f has to be differentiable, g has to be differentiable, the point has to be in the domain of f, and obviously in the domain of g. So we're going to see just real quickly how we might apply this idea. But right there is the idea. And that's really all there is to it as far as a constraint on a function of two variables and a maximum of another function. Constraint due to function g, the maximum of a function f.